Welcome to Lecture 8. This is the first part of 3. I'm going to be talking about input data analysis and fitting distributions. Before we begin, you need to make sure you have RStudio for the files. You can use R and just copy and paste out some of the code, but I think RStudio is going to be a lot easier. It'll allow you to generate documents in the format that this one is in. You can open up what's called an RMD file, which is what is posted here, and that can generate nice PDFs and also HTML documents like the one you're looking at. Okay. In this lecture, we're going to be learning how to choose a distribution to represent data. The big picture here is this is an art. There's no way that you can guarantee the correct distribution because of the underlying uncertainty. So there's going to be basically many different choices that you can use. And then combining with that is we have to assess how well any particular choice of distribution models the data. And this assessment piece is something that we're going to talk about in the next section. The first part of what we're going to talk about today is actually this, the probability distributions, some of the ones that we can use. So, one of the things I want you to take away from here is that while we're going to do our best job to do this, when you work on any real project, you should always find a statistician to consult. Unless you've gotten the training to have expertise at modeling data, it's always wise to consult at least with a statistician who does this for their primary job. Okay, so today we're going to be talking about, or in this lecture, we're going to be talking about fitting distributions, and some of the things we're going to talk about. For each one, we're going to talk about the density function, their CDF, which is their cumulative distribution function. Remember, the density function is the function that tells you, for a continuous distribution anyway, roughly the likelihood of something, of a value occurring. The cumulative distribution function is, and so we can say this in terms of like f of x here. We talk about a little f of x here, and we talk about capital F of x here. And the way you can think about this is that for a continuous distribution, the way you can think about this is that the probability that this random variable x is in a little, say, interval around a, so maybe a minus epsilon, a plus epsilon, what this is approximately equal to is f at a. Okay. Note that the probability that x, if it's continuous, equals a is always 0. So keep that in mind. So we have to always talk about it with a continuous random variable that it's in a little tiny interval. F of x, the way we think of this is the probability, remember, that x is less than or equal to a is equal to f at a. And of course, f at a also equals the integral of negative infinity to a of little f of x dx. Okay, that's their relationship. Okay, so one is the integral of the other. And of course, this is all when we're talking about continuous distributions. Okay, so that should all be review from SM 239. Okay, the key goal here is, now that we have some of this information, is to understand when a particular distribution is applicable and from the context, and when it's applicable from examining the input data itself. And we're going to talk about complexity here too. And complexity, of course, is a very context-laced definition where we're going to talk about what that means. Before I get into the continuous, I wanted to mention the finite discrete distributions. Okay, this is sort of when you have frequencies, frequencies of a discrete set of events. Think about coin flipping or rolling a dice, or the the likelihood that if you sampled a midshipman out of our class, they would be a male or a female, or they'd be a third class or a second class or a first class. I guess in our class that might not be. But anyway, you can count the frequencies of those events occurring just within your sample population, and then that's going to be the probabilities for your discrete distribution. That's the idea. Okay, so the setup here is that we might think of S. This is the set of values that this discrete distribution can take. And M is going to be the probabilities that these occur. With PIs, if you sum all those probabilities, they have to be equal to 1. And remember that PIs are non-negative because they're probabilities. And we say that the probability that X equals VI is equal to PI. The mean and the variance are just given by these two formulas here. And here's an example of that. So you should run through that calculation and make sure you understand it. Okay. So when do we use this, the finite discrete distributions? They're going to be modeled when we have a finite set of outcomes and some sort of data-driven understanding, usually, that the likelihood of each outcome, and you can either do that by the proportions observed in collected data, or maybe you just do it at random if you don't really have much information, but there's only two possibilities. Okay. Sometimes you want to just bootstrap too. So instead of doing the fitting of a data, what you could do is you could just take your data set and make each observation equally likely and just sample with replacement from that data set. That's called bootstrapping. It's done quite a bit. Okay. We'll move on to our first continuous distribution, the uniform and triangular. We've already been using these. Remember, uniform 0, 1 is our model for a random variable, or a random number, I should say. And triangular is this other, is similar to a uniform. Okay, so the uniform has this density function. Again, this should be review. You can look at this distribution function here. That's the CDF. And it has the following mean and variance as given by these formulas. Okay, and here's an example. Again, go through these examples to make sure you understand how the formula matches up here. The triangular can be viewed as sort of a generalization of the uniform. If you think about it, if you look back at this mean, right, this is basically the mean here is in the midpoint of the interval, right? Which makes sense. If you want to, if you take a uniform distribution and everything's equally likely on an interval, then the midpoint of that will be the mean. But perhaps you have some better understanding of the mode, really. Note that the mode and the mean are not the same thing, but it's, for the sake of argument, we might estimate the mean by using the sample mode. And when we have that, what's nice about a triangular is that we can specify it anywhere within that interval. It changes, of course, the density functions and the CDF as follows. And you can see there's an asymmetry around the mode when the mode is not in the midpoint of the distribution. When the mode is in the midpoint, then it actually, the two functions become symmetric in a sense. Okay, and then now we have a mean and variance. You should note that the mean looks a little similar, but it's just affected by this mode. And just note that mode and mean are not the same thing. However, a lot of times we do use the sample mean to estimate the mode. Okay, so here is some R code again. And we're going to now be able to plot our distribution so we can get a sense of what they look like. And you can see that the uniform distribution is the one in blue. You can see it's just uniform, like that straight line across, of course, makes it so that everything is equally likely on the range. And then the triangular, you see why it gets its name, right? It has this triangular shape in red here. Okay. The CDFs, you can see the uniform it does something sort of interesting. It just goes straight up. That's that blue line again. And then the red line is the triangular. You can see it has more of an asymptotic flavor to it. And that's, again, because of it's a little less likely to be less than the mode on each of these points, and more likely on the points above the mode because of where the mode is. That curve would change if you had the mode less than the midpoint. So when do we use uniform? Well, generating other distributions. Well, in fact, we've already talked about this. When we use the inverse transforms. When you need a bounded distribution and all the possibilities are equally likely. Or in low information situations. Maybe if you just arrive at a subway platform during a non-busy period and you don't know when the last train arrived. So triangular distributions are sort of used when you have slightly more information, but still low information. But the one difference between that and the uniform is you have some good guess at this mode. Okay. I'll note that all these also can be used for situations when you have negative values. Let's talk about the exponential. The first thing I'm going to note is the exponential distribution is a special case of the gamma distribution. And both of them are often used to model wait times. So for the gamma distribution, we have this gamma function, and it has two parameters. Remember, it has the shape alpha and a rate beta. So the gamma function, which is what gives us its name, is this kind of weird looking function here. This gamma of z is equal to this integral over from 0 to infinity, x raised to the z minus 1th power, e to the minus x dx. Okay. If z is an integer, it turns out that the gamma function is the same thing as factorial. The density function is defined for x greater than 0 is the following. So it has this looking this fellow that looks like that, and you can see it has the exponential. You should see it, and you should think of yourself, well, that does look a little exponential. The only difference is it does have this gamma function in terms of the shape, and the rate occurs over here. You can see, again, the rate and the mean are going to be related. CDF is found by integrating, and when you integrate, you get this, you just compute the integral of that function. It can be a little nasty, but it can be done. And then I want to note that the domain of the density is positive real numbers. In other words, the gamma and exponential are non-negative. And they're used for non-negative random variables. Okay, so how is the exponential similar? When alpha is 1, when the shape is 1, then the gamma is in fact the exponential. Okay, so let's look at their shapes again. You can see that these first two, the red and the gold lines there, those are both, so it's the one here and here. These are actually just exponentials. But the gammas, the non-exponential gammas here, you can see they have all sorts of different shapes, and they've been used to model a variety of different things. Okay, so exponentials kind of start off on this high peak, and then they go down low, and then they just kind of go to 0. Gammas have extra sort of bulbous or extra curvature in them. Okay, so they're useful for a wider variety of situations. I should note that, and I'll start to talk about this here, is that the complexity of the gamma is higher because it has two parameters. So I should note that gamma has two parameters, and that's what we mean when we say it's more complex than the exponential with one parameter. Just like the uniform is less complex than the triangular because the triangular has 3 parameters, whereas the uniform only has 2. We tend to prefer a simpler model, one with fewer parameters, if it does the trick. Okay, here are the CDFs. Again, you can see that the exponentials look quite similar. They're just going to kind of have these slight different. They're going to have these differences in where they start to get asymptotic, but the shape is going to look the same. Whereas the gammas can look in a variety of ways. Okay. The last family of distributions I'll talk about is the normal distribution. This is perhaps the most significant because of the central limit theorem. If we assume finite variance, independent samples of any distribution converges to a normal distribution over time. So if you get enough samples, all distributions start to look normal under the assumptions of the central limit theorem. Very powerful theorem, one of our most important ones. It has a density function given by here. It looks kind of nasty because of that 1 over square root of 2 pi sigma squared. It's specified. You give the mean and you give the variance, and then it spits out the function. So it's also quite nice because of that. You integrate the density to get that. Usually you have to do that numerically. There's not a closed form way of writing it down. So the domain of the density function and the cumulative density function is actually the whole real line. So it varies from negative infinity to positive infinity, and it just kind of shifts around where this is this sort of common bell curve. It just shifts where it is depending on the mean. The standard normal is when the mean is 0 and the standard deviation is 1. And here we have the sort of what you have probably seen before with the bell-shaped curves. This is not shape and rate. Of course, this is going to be mean and standard deviation. Okay, I'll correct that before I post this. So you'll see a corrected one on a version of these slides on the classroom. Okay, and that's just sort of your ordinary bell-shaped curve. The cumulative density functions, again, look like this. I imagine you've seen them before. And I'm just going to note that there's all these clever ways that we have here of sort of plotting these. This uses something called ggplot. It can be very helpful. Why do we want to plot distributions when we know them? It's so that when we construct histograms, we can look at the different shapes. And we'll talk about that later on in the further parts of this lecture. Okay, so when do we use the normal distribution? We use it in situations where you're averaging or you're summing up many things. And we use it for measurement errors, stock market indices, and even standardized test scores. Anytime when you have a lot of samples and then you start to be able to apply the central limit theorem. So what I'm going to tell you all to do, so you've been listening to me talk about other stuff, but open up that RMD file and play with this code. Make sure it runs on your computer. Make sure you can get these shapes. Okay, this is sort of the first step in this input distribution so that we can start to visualize. And so you start to get comfortable with R again. We've been using Simio up until now, and now we have to switch gears and start using R as well.